Hey, good morning. Welcome again to Humke's Study. Today I thought we'd take a look at the problems that we were talking about yesterday. So here's one. This will be an M3 by 2. And it would be a question like this. So I'll give you a set of things. So we'll look at the span of a certain set of vectors. And I've got these down here. These vectors will be in here. This is our vector space that we're talking about. So here they will be 3, 2, 1, minus 1, 1, 4. There are 4 of these guys. 0, 3, 4, 1, 2, 2. The next one is 6, 1, minus 2, minus 3, 0, 6. And the last one, fortunately, is minus 3, 1, and then 3, 2, and then 1, minus 2. And we want where t is the span of this, and I could ask the following kind of questions. The first one might be something like, find a basis for t. So you'll want to sweep out any of the dependencies. Or I could say, compute the dimension of t. So again, you've got to find a basis for t and then just count the number of things. So this kind of question all can be answered in the same way. And I wanted to sort of show 2 ways to do this. Basically, what we want to do is find out how many independent vectors there are here. And these are matrices. So I'll call this M1, M2, M3, and M4. So so finding a basis, we're going to look at we're going to look at the equations. I'll use x and y. X times M1 plus y times M2, maybe x2 times M2 plus x3 times M3 plus x4 times M4 equal to 0, the 0 vector, the 0 matrix here, 0, 0, 0, 0, 0, 0. And we want to find out how many independent variables. How many independent variables? So let's write this out. There's a lot of writing in this case, but x1 times m1 will be, this is a scalar multiple times m1, so this will be 3x1, 2x1, x1 minus x1, x1, 4x1, plus x2 times m2, so 0x2, 3x2, 4x2, x2, 2x2, 2x2, plus 6x3, x3 minus 2x3 minus 3x3, 0, 6x3. And then finally, the x4 one, this will all be equal to the 0 matrix, 0, 0, 0, 0, 0, 0, minus 3x4, x4, 3x4, 2x4, x4, minus 2x4. I'm going to add all these up and set it equal to the 0 matrix, and we'll see what we get. I'll try to leave these up here and work above. So adding these up, in the first position, I'll get 3x1, no x2, 6x3, and minus 3x4. That's in the very first position. In the position next to it over here, I get 2x1 plus 3x2 plus x3 plus x4. The next row will have x1 plus 4x2 minus 2x3 plus 3x minus 2x3 plus 3x4. And then the next one we get minus x1 plus x2 minus 3x3 plus 2x4. The last row, x1 plus 2x2 plus 0x3 plus x4, and then 4x1 plus 2x2 plus 6x3 minus 2x4. And this is supposed to be equal to, we'd like to solve this equal to, maybe I'll put this over here. I want to solve this equal to 0, 0, 0, 0, 0, 0, the zero vector in this M3x2 space. This will give us 6 equations in 4 unknowns. 6 equations in 4 unknowns. The first equation is 3x1 plus 6x3 minus 3x4 equal to 0. The next equation is 2x1 plus 3x2 plus x3 plus x4 equal to 0, and so on. So we want to solve this system of equations. Maybe I'll write the next one just to be clear. The next one is x1 plus 4x2 minus 2x3 plus 3x4 equal to 0. So we want to solve this system of equations, see how many independent variables there are. So this reduces it to 6 equations in 4 unknowns. So I solved this with Mathematica earlier, and there, in this case, there are exactly 2 free variables and 2 dependent variables. So there are 2 free variables. So there are 2 dependent variables. So they are, since you've got a free variable, they are not linearly independent. And since you've got 2 free variables, 2 of these are independent. There are 2 that are independent, and the 2 that these pick out are the first 2. And we'll take a look at that Mathematica in a little while. So this is one way to do it, kind of using the definitions, using the fact that these are vector spaces, multiplying through by the scalars, which were variables in this case, and adding them up using the method of adding in M3x2, and then solving the equations that you get. So this is one method. There's a little more method that's a little more direct. You need to know a little bit more to do the second method, but we sort of do already. And so this could be the second method. If you look at M3x2, this is analogous to, in the sense of vector spaces, this works the same way as this familiar space. So on the right here is a sort of familiar ground, six-dimensional real space. This is a matrix space. These are different objects than these. These are vectors. These are matrices. But we can utilize this, the fact that as vector spaces, they operate the same. And we talked about this correspondence, how this goes. So this 3 by 3 matrix, 3 by 2 matrix corresponds to the vector. I'll write it as a column, A, B, C, D, E, F. So if you use this correspondence matrices adding up corresponds to vectors adding up and so on. So we can look at this in this space, solve the problem in this space, and then translate into this space. And in this case, it's pretty straightforward. So here we have then the 4 vectors corresponding to these, and 3, 2, 1, minus 1, 1, 4 times x1 plus x2 times 0, 3, 4, 1, 2, 2 plus x3 times 6, 1, minus 2, minus 3, 0, 6 plus x4 times minus 3, 1, 3, 2, 1, minus 2 equal the 0 vector. We want to see how many independent, how many dependent variables you have when you solve the system. So this is a vector equation. I mean, this is in a way no different than the one we just had. We're again going to get 6 equations and 6 unknowns. The first equation will be 3x1 plus 0x2 plus 6x3 plus, well, minus 3x4 equal to 0. And that's the first equation we got the last time. So in a way, this is structurally going to give us the exact same equations. It's not a surprise that it does, but we are set up already to do this. So we can solve this vector equation pretty quickly now. I'll erase this and then set up the vector equation. Because the vectors 3, 2, 1, minus 1, 1, 4, 0, 3, 4, 1, 2, 2, 6, 1, minus 2, minus 3, 0, 6, minus 3, 1, 3, 2, 1, minus 1, augmenting with zeros, reduced row echelon form. And when we reduce this in row echelon form, this is what we get. Let's see if I've still got it up here. So just that I can't read it. So I'll share this here. So here's what we get. 1, 0, 2, 1. And 0, I neglected in what I did, I didn't actually add on the 0 column. 0, 1, minus 1, minus 1. 0, and then all the rest are zeros. So throughout this area, you get all zeros. So there are 2 pivot positions, here and here. And so for this, there will be exactly 2 of these vectors that are linearly independent of each other. This picks out the first 2 here, the pivot positions. These 2 are, we have to unshare now. So this matrix, when it reduces to this, you have exactly 2 pivot positions, pointing out that these are the 2 vectors that are independent, these 2 are dependent on these, and as a consequence, these two span the corresponding set here to the original set of matrices. So that will tell you that these two matrices are linearly independent. They form a basis. These two are, the last two are dependent on the first two. So the dimension of T is 2. A basis for T consists of these two vectors. So this is this correspondence is nice to use. And I thought I'd just do one more problem here that is very similar. And that problem involves, so this is problem 2. We're going to talk about the polynomial space P3, cubic polynomials. I'm going to give you a set of cubic polynomials. 3 plus 2x plus x squared minus x cubed is the first. And the second one is 3x plus 4x squared plus x cubed. The third polynomial is 6 plus x minus 2x squared minus 2x cubed. And the last one is minus 3 plus x plus 3x squared plus 2x cubed. And we want to ask the same questions. We'll look at the span of F. And what is a basis for the span of F, for the subspace generated by this set of functions? And what is the dimension of this? Both of those require the same sort of information. And so how do you work this problem? I would look at P3, and I would say, we've sort of looked at this. This has a standard basis of constant x, x squared, and x cubed. So this is 4-dimensional space. It is associated with R4. So these two work alike as linear spaces, and we can use this information. So again, if you take a plus bx plus cx squared plus dx cubed, this corresponds to the vector A, if I write it as a column, A, B, C, D. It is those 4 numbers that, in order, that characterize this polynomial. I'll give you exactly what that polynomial is. This is not a polynomial. This is something like a code for this polynomial, and you can work with the codes to understand what the polynomials are doing. This was the same theme that we had when I used a matrix to find the derivative of a polynomial. You're using the code and the matrix representation of the derivative function in order to find the derivative mechanically. All right, so how does this go? How do you do this problem? Well, we'll translate from polynomial space into R4. And the first polynomial, F1 here, that polynomial translates into 3, 2, 1, minus 1. And the second polynomial translates into 0, no constant, 3, 4, 1. The next one, 6, 1, minus 2, minus 2. And the last one translates as to minus 3, 1, 3, 2. So this collection of functions, of polynomials, is coded or described by this collection of vectors. And so what we want to do is we want to see how many of these are independent, how many of these are, where are the dependencies here? So we'll set up the corresponding matrix, we'll row reduce it, and look at the pivots. 3, 2, 1, minus 1. 0, 3, 4, 1. 6, 1, minus 2, minus 2. and then -3, 1, 3, 2. Okay, so now we want to row reduce this guy, see what we get. So I'll use Mathematica to row reduce. And when we row reduce this, we get 1, 0, and I forget what these numbers are, but we get 2 numbers here, 0, 1, a couple numbers here, and then all the rest zeros. So we have 2 pivots corresponding to the very first 2 vectors that we had. So these 2 vectors form a basis for the space in R4 that corresponds or codes this space. And now decoding these gives these 2 functions. So F1 and F2, these 2 functions will be a basis for F. These 2 are dependent on these 2. And the dimension of F is 2 because there are 2 things in the basis. So this is the whole ball of wax, how to use this coding or this relationship between R4 and P3 in order to solve these problems in P3. Hang on for just a second.